All right, hello everyone, and welcome to my channel. This is a channel for educational purposes. We try to tune into some of the greatest theories of everything that I know of from many years of research, digging around, curiosity, and trying to bring to you things that you may not know about, but that if you did know about them, they would benefit your life in countless ways, help you with your new paradigm formation, your preparation for 5D consciousness. Today is our 418th video on the reciprocal system of theory. And this is a system of theory that was first originated by Dewey B. Larson. And in 1959, Mr. Larson proposed his two fundamental postulates, which was a product of him boiling down all of his research from the last 20, 25 years, 30 years even, of trying to figure out how the universe operated. He had a few epiphanies and a few leads, and he worked it out over the course of time. And then he took those two fundamental postulates and derived, through a process of deduction, a long process of deduction, he derived a theoretical universe about how the universe would look if the universe operated the way that he said that it does. And then in his books, he compared his theoretical universe with the empirical universe, the measured universe of the legacy scientists that they have, measured in their laboratories and compiled in their scientific tables. And we are looking at one of the results of that effort, which is called Basic Properties of Matter. This book is primarily about chemistry, and it looks at some of the basic properties of matter and compares Larson's theoretical results. He derives equations for each one of the basic properties of matter, or a number of equations in some cases for the basic properties of matter, and then compares them with the scientific tables. And we are in chapter 2 of this book. I think this is the third or fourth installment of this, fourth installment of this chapter, and about the 13th installment of the whole book. And this chapter is on inter-atomic distances. So the two fundamental postulates of Larson are: one, the universe is composed primarily of, or not primarily, entirely. The universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with two fundamental two reciprocal aspects, space and time. And the second postulate is more mundane, that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So the second postulate is just kind of almost a priori, like the way that you have to pretty much just say, well, 2 plus 2 equals 4. We have to, the laws of math work the same, today as they did yesterday. So it's kind of just, you have to agree to the second postulate almost just in order to do science. But many people have disagreed with the second postulate, including me, in terms of the Euclidean geometry. I have been convinced that there are other forms of geometry that are more inclusive. Projective geometry, in fact, includes Euclidean geometry as a subset. So Bruce Perret, among others, has proposed an alternative second fundamental postulate that gets rid of the commutative mathematics and the absolute magnitudes and the Euclidean geometry. I'm pretty much on board with that, but I don't really think it's all that important at this point. The first postulate is the real breakthrough for Larson, and I could restate that as just saying, you know, the universe is not made out of matter, it's not made out of energy, but it is made out of motion. And in particular, it's made out of a kind of motion that is called scalar motion. Scalar motion is a more generalized and a non-localized motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision scalar motion if you take a balloon and with a magic marker you put dots on the balloon. If you blow up the balloon, all of the dots will be moving away from each other. That is a scalar motion. There is no specific direction. Every dot is moving away from every other dot. There is no, way to mark the directions there. The only way that you'd be able to do that is to assign a reference point. That is to say that one of the dots arbitrarily is motionless. And by, saying that one of the dots is motionless, then you can start, measuring the directions to the other dots. And so this scalar motion is really the motion that is of what the universe is constructed. You can see that if you look at first, that motion is the relationship between space and time. So that is where Larson gets the name the reciprocal system of theory. Space and time are reciprocals of one another, generally. They have identical qualities, but in different order. The same way that 3/1 and 1/3 are reciprocals of one another. They have the same qualities, but they are in different order. And motion is basically a fraction, with space or time as the numerator, time or space as the denominator. All of our basic scientific quantities are motions. Matter is a motion, energy is a motion, acceleration is a motion, momentum is a motion, force is a motion. And they all have different time-space coordinates, or, spaces on the fraction. Because both time and space can come in three dimensions, or even more. But Larson says the universe is made out of motion, and motion can come in 3 dimensions. He calls that coordinate space and coordinate time. So also a spatial reference system and a temporal reference system. Think of X, Y, Z coordinates or volume in space in a still frame. That would be your coordinate space, and 3 dimensions of time in a still frame would be your coordinate time. 3 dimensions of space and time. So, for example, matter is time to the 3rd power over space to the 3rd power. Energy is time over space. Speed is space over time. Acceleration is space over time to the 2nd power. And you can come up with those time-space coordinates for all your basic scientific quantities, which is a huge improvement over the MKS system, where you have 3 different qualities or quantities. You have mass, and then you have space and time, the MKS system, meter, kilogram, second. And so now you can just take that kilogram of mass and you can turn that into t to the 3rd power over s to the 3rd power. And so now you're just dealing with 2 variables instead of 3. Now also another important prong of the first postulate is that space and time come only in discrete units. They are quantized. You have to have a full unit before you have anything. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. If you have 1 unit of space in 1 unit of time, 1 over 1 equals 1. Larson calls that unit speed. Unit speed is also the speed of light. And so this speed of light is the center of Larson's universe. In order to basically embark on a study of the reciprocal system, you have to be able to be okay with the concept of motion existing without anything moving, without anything. Motion exists before anything that would be moving. And in fact, the thing that would be moving is motion itself. And so in Larson's empty universe, or his zero point, or his null point origin of the universe, is the speed of light outward in all directions. Scalar motion, just like on an expanding balloon, outward in all directions. And that occurs in both space and time. And then Larson calls that the progression of the natural reference system. You can kind of think of it as the flow of time, the flow of space. The progression of the natural reference system. Now, if you suck in that balloon, that's the opposite force. The contracting balloon, where all of the dots are moving toward each other, that is akin to gravitation. Again, though, that doesn't imply a gravitational field. You only can get a gravitational field when you assign a reference point, and when you say that one of these dots is motionless. And then you can start looking at the relations between the individual dots. Before then, it's just all the dots are moving toward each other. Now, within the discrete unit postulate, it sets up a boundary between the unit speed boundary. So it sets up 2 different sectors of the universe, a material sector and a cosmic sector. In the material sector, the motion is slower than the speed of light. In the cosmic sector, the motion is faster than the speed of light. And they are reciprocals of each other. In the material sector, you have relations based on 3 dimensions of space in a still frame and progressing or flowing time. Time is always getting farther and farther and farther apart. And then in the cosmic sector, when you cross that speed of light boundary and go to faster than light speed, then you have relations based on coordinate time, 3 dimensions of time in a still frame, and clock space, the flow of space. Space is always getting farther and farther and farther apart, just like on the surface of an expanding balloon. Now, but what this also does is within each of those sectors, Larson calls those the material sector and the cosmic sector. Within those sectors, you also have a subregion. Again, due to the discrete unit postulate, within the material sector, if you have interactions that are based in less than 1 unit of space, you don't have space. You have to have a full unit. So if you don't have a full unit, you don't have space. And so you only have time. And so that is what Larson calls the time region. And when you cross that unit distance boundary, you change the rules again. The rules change and the directions change. The progression now becomes inward and gravitation becomes outward. Same is true in the cosmic sector, except with time instead of space. When you have interactions that occur in less than 1 unit of time, then you don't have time and you only have space. And Larson calls that the space region. And in the space region, gravitation moves outward in space, and the progression moves in. The progression moves inward in time. And these 2 regions are these are the realms of atomic and molecular interactions. So that is relevant here, where Larson is discussing the interatomic distance. The interatomic distance is basically an equilibrium that is established within the time region, where the constant motion of the progression of the natural reference system, which is inward, is balanced by gravitation, which is outward, which is variable. So you have to figure out the distance at which gravitation becomes equal to the progression. Okay, so we'll go from there. We'll see what happens here. We went through a few of the groups of atoms, and he kind of did compare his results. But now we're going into division 3, which is Larson divides the periodic table into 4 divisions. Division 1 and 2 are electropositives on the left side. Division 3 and 4 are on the right side, electronegatives. Division 2 and Division 3 maintain a valence of 4 or more. And so that's kind of how that goes. Because of the greater probability of the electropositive types of combinations, the characteristics of Division 2 carry over into the first elements of Division 3, and these elements, nickel, palladium, and lutetium, are included in the table. Some similar modifications of the normal division boundaries have already been noted in connection with other subjects. The net total rotation of the material atom is a motion with positive displacement. That is, a speed less than unity. And as such, it normally results in a change of position in space. Inside unit space, however, in the time region, all motion is in time. The orientation of the atom for the purposes of the space-time equilibrium therefore exists in the 3 dimensions of time. As we saw in our examination of the interregional situation in Chapter 12 of Volume 1, which is called Nothing But Motion, Each of these dimensions contacts the space of the region outside unit distance individually. So each one of the dimensions is independent. To the extent that the motion in a dimension of time acts along the line of this contact, it is a motion in equivalent space. Otherwise, it has no spatial effect beyond the unit boundary. Because of the independence of the three dimensions of motion in time, the relative orientation of the electric rotation of any combination of atoms may be the same in all spatial dimensions, or there may be 2 or 3 different orientations. In most of the elements that have been discussed thus far, the orientation is the same in all spatial dimensions, and in the exceptions of alternate rotations, the alternate rotations are symmetrically distributed in the solid structure. The force system of an aggregate of such elements is isotropic. It follows that any aggregate of atoms of these elements has a structure in which the constituents are arranged in one of the geometrical patterns possible for equal forces, an isometric crystal. All of the electropositive elements, divisions 1 and 2, crystallize in isometric forms. And except for a few, which apparently have quite complex structures, each of the crystal forms of these elements belongs to one of or another of 3 types: the face-centered cube, the body-centered cube, or the hexagonal close-packed structure. We now turn to the other major subdivision of the elements, the electronegative class, those whose normal electric displacement is negative. Here, the force system is not necessarily isotropic, since the most probable arrangement in 1 or 2 dimensions may be the negative orientation, a direct combination of 2 negative electric displacements, similar to the all-positive combinations. Just as an editorial here, you can see as Larson moves through these different subjects that probability takes such a large importance in his deductions. Okay, he's always he's using a deductive process, if this then that, to construct his theoretical universe, and in doing so he uses the probability principles and recognizes that what happens is the most probable thing. Or if there's close probabilities between 2 things, then maybe 2 different things can happen. But he has to apply the principles of probability to determine the if this then that aspects of many of his derivations of deduction. Okay, so division 2 is not necessarily isotropic, and 1 or 2 dimensions may be negative, the negative orientation, a direct combination of 2 negative electric displacements, similar to the all-positive combination. It is not possible to have negative orientation in all 3 dimensions. And wherever it does exist in 1 or 2 dimensions, the rotational forces of the atoms are necessarily anisotropic. The controlling factor is the requirement that the net total rotational displacement of a material atom as a whole must be positive. Negative orientation in all three dimensions is obviously incompatible with this requirement, but if the negative displacement is restricted to one dimension, the aggregate has fixed atomic positions in two dimensions, with a fixed average position in the third, because of the positive displacement of the atom as a whole. This results in a crystal structure that is essentially equivalent to one with fixed positions in all dimensions. Such crystals are not usually isometric, as the interatomic distance in the odd dimension is generally different from that of the other two. Where the distances in all dimensions do happen to coincide, we will find on further investigation that the space symmetry is not an indication of force symmetry. If the negative displacement is very small, as in the lower division 4 elements, it is not possible to have negative orientation in two dimensions if the positive displacement in the third dimension exceeds the sum of these two negative components, so that the net result is still positive. Here, the relative positions of the atoms are fixed in one dimension only, but the average positions in the other two dimensions are constant by reason of the net positive displacement of the atoms. An aggregate of such atoms retains most of the external characteristics of a crystal, but when the internal structure is examined, the atoms appear to be distributed at random, rather than in the orderly arrangement of the crystal. In reality, there is just as much order as in the crystalline structure, but part of the order is in time rather than in space. This form of matter can be identified as the glassy or vitreous form to distinguish it from the crystalline form. So he's saying that the glasses are cases of mixed positive and negative orientation. And so some of the order is now in time instead of space. Okay, so the term state is frequently used in this connection instead of form, but the physical state of matter has an altogether different meaning based on other criteria, and it seems advisable to confine the use of this term to one application. So both glasses and crystals are in the solid state. In beginning a consideration of the structures of the individual electronegative elements, we will start with division 3. The general situation in this division is similar to that in division 2, but the negativity of the normal electric displacement introduces a new factor into the determination of the orientation pattern, as the most probable orientation of an electronegative element may not be capable of existing in all three dimensions. As stated earlier, where two or more different orientations are possible in a given set of circumstances, the relative probability is the deciding factor. Low displacements are more probable than high displacements. Simple orientations are more probable than combinations. Positive electric orientation is more probable than negative. In division 1, all of these factors operate in the same direction. The positive orientation is simple, and it also has the lowest displacement value. All structures in this division are therefore formed on the basis of the positive orientation. Division 2, in division 2, the margin of probability is narrow. Here, the positive displacement x is greater than the inverse displacement 8 minus x. And this operates against the greater inherent probability of a simple positive structure. As a result, both the positive and reverse types of structure are found in this division, together with a combination of the two. In division 3, The negative orientation has a status somewhat similar to that of the positive orientation in Division 2. As a simple orientation, it has a relatively high probability, but it is limited to one dimension. The regular Division 3 structures of group 3A and B are therefore anisotropic. With the reverse orientation in the other two dimensions, a combination with the reverse orientation in the other two dimensions, the anisotropic of 3A and 3B of Division 3. A combination of these two types of orientation is also possible, and in copper and silver, the first Division 3 elements of their respective groups, the crystals formed on the basis of this combination orientation have cubic symmetry. As to Division 2, the elements of Division 3 in groups 4A and 4B crystallize entirely on the basis of the reverse orientation. Table 4 lists what may be considered as the regular interatomic distances of the elements of Division 4. Division 3. Although the probability of the negative orientation is greater in Division 4 than in Division 3 because of the smaller displacement values, this type of structure seldom appears in the crystals of the lower division. The reason is that where this orientation exists in the elements of the lower displacements, it exists in two dimensions, and this produces a glassy or vitreous aggregate rather than a crystal. The reverse orientation is not subject to any restrictive factor of this nature, but it is less probable than the lower displacements, and except in group 4A, where it continues to predominate, this orientation appears less frequently as the displacement decreases. Where it does exist, it is increasingly likely to combine with some other type of orientation. As a result of these limitations that are applicable to the inherently more probable types of orientation, many of the Division 4 structures are formed on the basis of the secondary positive orientation, a combination of two 8-x displacements. All right, we're going to stop there. Hang in there. We just got to get through this, and we'll make sense of it later. So hopefully you'll join me tomorrow and continue this chapter. Thanks for tuning in.